Okay, so we're going to do a a surface integral of a vector field. We're going to do problem number 1 here, 12.1. Okay, so the line integral of a vector field, the surface integral of a vector field over a surface. So this is what we're doing. So I should say, but I mean with outward orientation, this is equal to the line integral of the scalar field f dotted with n ds, where n is the outward pointing normal vector. Okay, if we had inward orientation, n would need to be the inward pointing normal vector. But the standard thing is to take the outward pointing orientation, the outward orientation. So actually, I do say it right here, outward orientation. Okay, and now remember, what is the surface integral of a scalar field? Well, this is the scalar field that we're integrating, f dotted with n, and now we multiply this by rs cross rt ds dt, and we do the integral over the parameter domain. Oh, sorry. We do the integral over the parameter domain d. So f dotted with n is a scalar valued function. It's like the little f from when you're doing a surface integral of a scalar field. Okay, so this is f dotted in evaluated at the parameter at the parameterization. I didn't put it there, times the magnitude of rs cross rt ds dt. So there's a lot of steps that you have to go through. There's a lot of places to get lost. So we're just going to go through this. Do number 1 kind of very slowly and deliberately here. Okay, so the first thing we need to do is compute f dotted with n. That is a scalar field that we're going to be taking the surface integral of. So for n, we need to come up with a normal vector. So to come up with a normal vector, you want to guess that the normal vector is going to be something like, so our parameters in this problem are going to be x and y. You'll see now, you'll see why in a minute. It's actually, before, let me just get the parameterization for the okay, to find the normal vector, you need the parameterization for this surface. So let me just do the first things first. So the parameterization for this surface, it's an upside down facing paraboloid. R of xy, R and xy are going to be the parameters. This is x, y, 4 minus x squared minus y squared. And the parameter domain D, well, x goes from 0 to 1 and y goes from 0 to 1. The parameter domain is just going to be 0, 1 cross 0, 1. Okay, so this right here, if you're not familiar, this is just shorthand notation for x goes from 0 to 1 and y goes from 0 to 1. Okay, so since the parameter domain is a square like this, I'm going to keep it in Cartesian coordinates. If the parameter domain was a circle, then I'd probably do this in cylindrical coordinates, okay? But since the parameter domain is a square, I'm going to keep it in rectangular coordinates or Cartesian coordinates. Okay, now in the normal vector is either going to be Rx cross Ry over the magnitude of Rx cross Ry, or it's going to be negative this. In other words, it's going to be Ry cross Rx over the magnitude. Okay, so to figure out which one, we're just going to take a guess, say Rx cross Ry, see if this gives the outward pointing orientation. If it does, this is the right guess. If it gives the inward pointing orientation, we just multiply it by -1. So no matter what, this right here is either going to give you the outward normal vector or the inward normal vector. If it gives the inward normal vector, you just have to multiply it by -1. Okay, so Rx is equal to 1, 0, minus 2x. This is just the derivative with respect to x. Ry is equal to 0, 1, minus 2y. And we're going to guess that Rx cross Ry, that's going to give the outward pointing normal vector. So actually, let me come over here to do it. Rx cross Ry. I will let you do this on your own, but this is 2x, 2y, 1. And the magnitude of Rx cross Ry is equal to the square root of 4x squared plus 4y squared plus 1. Okay, so then our guess, Rx, cross ry over the magnitude of rx cross ry is equal to 2x, 2y1 over the square root of 4x squared plus 4y squared plus 1. Okay, so now we want to check at one point. All you have to do is check at one point to see whether or not this is outward pointing or inward pointing. So let's check at the point 0, 0, 0. Or sorry, 0, 0, 1. X is equal to 0, y is equal to 0, 1 is equal to 0. This is a downward facing paraboloid, so the normal vector should be pointing straight up. Okay, so if x is equal to 0, y is equal to 0, this is 0, 0, 1 over 1. So if x and y are both equal to 0, this vector is this vector here is 0, 0, 1. And that's what we want it to be. It's upward pointing. If we'd done ry cross rx, we would have gotten 0, 0, negative 1. That would have been the downward pointing normal vector. So we would have multiplied it by 1. But this is the upward, this is the outward pointing normal vector. So in is equal to 2x, 2y1 divided by the square root of 4x squared plus 4y squared plus 1. Okay, so what have we done? We have computed the scalar field. We now know in. We can do f dotted within to get the scalar field that we're going to be integrating. So f is f here is xy, yz, zx. So f dotted within is equal to 2x squared y plus 2y squared z plus zx divided by 4x squared plus 4y squared plus 1. Okay, so this is a scalar field, and we want to do the surface integral of this scalar field over this surface S. Okay, so now this is where we are. This is where we are. Now we're going to go to this step. So we have this. Now we're going to go to this step. Okay. So we need to evaluate f dotted within at the parameterization. In other words, at R. Okay. So what that means is we look at the parameterization. The x component is x. The y component is y. The z component is 4 minus x squared minus z squared. Okay. So wherever you see an x, we're going to put an x. Wherever you see a y, we're going to put a y. Wherever you see a z, we're going to put 4 minus x squared minus y squared. And this right here. So what this becomes, well, so first of all, the parameter domain D, x goes from 0 to 1, y goes from 0 to 1. So let me do that first. So this will be y goes from 0 to 1, x goes from 0 to 1. You could put the x integral on the inside if you want. Now we're going to put f evaluated at the parameterization, or f dotted within evaluated at the parameterization. That's this right here. So this is just going to be 2x squared y plus 2y squared. Okay, z is 4 minus x squared minus y squared. So this is 4 minus x squared minus y squared plus z times x. So this is going to be x times 4 minus x squared minus y squared divided by the magnitude. So this is the square root of 4x squared plus 4y squared plus 1. Okay, so that is, we've got the parameter domain. We've got the scalar field evaluated at the parameterization. That's what this part is here. Now we need to multiply by the magnitude of the cross product. Remember, this is the cross product, this is the magnitude. So now we're going to multiply sorry. Okay. So now we're going to multiply by the magnitude. So let me just scoot this over. So this will be times the square root of 4x squared plus 4y squared plus 1 dy dx. Sorry, running out of room, or I've ran out of room. Okay, but the whole point is that, or not the whole point, but the key thing is that this and this cancel, and so what we're left with is just the integral x equals 0 to 1, the integral y equals 0 to 1, 2x squared y plus 2y squared 4 minus x squared minus y squared plus x times 4 minus x squared minus y squared dy dx. Okay, and if you compute this, you get that it is 713 divided by 180. Okay, I mean, it'll be kind of tedious, but this is just an integral of a polynomial in the x and y variable. So there's nothing, I mean, it's straightforward, though it might be kind of tedious. Okay, so just to review, the surface integral of a vector field, this is the surface integral of a vector field. It is equal to the surface integral of a scalar field, f dot. Sorry, I thought I could save that cough. Anyways, this is the surface integral of the scalar field, f dotted within, and then we just know to go from this step to this step. This is just how we compute the surface integral of a scalar field. So you just have to go through step by step, fill in the thing that you need to at each point, check to make sure everything is right, and just kind of very much take your time with this.